Problem number 33. We wish to find the three partial derivatives with respect to x, y, and z of this function of cosine of y divided by xz squared. Now you could use quotient rule if you wanted to, but I decided to bring up that denominator as individual terms and just give them negative exponents, because I could always easily change them back to positive at the end. That'd be easy to do. But this way you can avoid the quotient rule, and there'll be no need for the product rule anywhere either. So I think this will be a little easier. So let's see what we have here. The x partial. So take the derivative of x will be negative 1 x to the negative 2 right here. Z to the negative 2 cosine of y. So I rewrote it with the x and z's on bottom because you can see that's how the answer choices are written. And let's see, for the fy partial, we'll take the derivative of cosine of y, which will be negative sine of y. So that negative here is a different reason for the negative than the negative above. It's from the derivative of cosine. So we have negative x to the negative 1, z to the negative 2, sine y. Drop the x and z to the bottom, so you have xz squared on the bottom. Now the z partial, we have negative 2 comes down. The z exponent becomes negative 3 cosine y. So we have negative 2 cosine y over xz cubed. And that's going to be, looks like answer C. I'll just put, usually I have these circled on some of the other ones, but I guess I don't on this one. So I'll just kind of dot them as we go. Actually, I stand corrected. It's answer D. Excuse me. It's answer D. Okay. So that takes care of 33. Number 34 wants the fxx partial only, which of course means we take the x partial and then just take the x partial again. So this one should be pretty easy. The fx partial then would be 4x cubed y7, and then take the derivative of x would be 5x4y. Then the next partial, 3 times 4 is 12, x squared y7. 4 times 5 is 20, x cubed times y. And there we have it. So it would be answer D. All right, that one was pretty straightforward. $35. The fxy mixed partial, which of course is equivalent to fyx. So you could have solved it in that order if you wanted to. But I went kind of the same order it's written. But we've learned the mixed partials are equal. So let's look at what we have. We have cosine of 4xy. So the derivative of that will be negative sine of 4xy times, via the chain rule, the derivative of 4xy with respect to x, because it's the fx partial. So the derivative of the inside 4xy with respect to x is going to be 4y. Now the negative, of course, comes from the derivative of cosine being negative sine. So there we have negative 4y sine 4xy. Well, that's created a bit of more of a challenge for the next derivative, because we have to do a product rule, because we have two functions of y multiplied together. So let's see what happens here. All right, so I go, you can go either order on the product rule because of the plus sign. I'm going to go this order. I'm going to take the derivative of negative 4y with respect to y. It's going to give me negative 4, and then the sine of 4xy, plus f, which is negative 4y, times the derivative of sine of 4xy, Now, I didn't quite write it out elaborately as I did here, but the derivative of sine of 4xy will be cos of 4xy times the derivative of 4xy with respect to y. So that would have just said partial respect to y of 4xy, but it is correct that I have 4x here. So I just consolidated the loose terms, and then we have negative 4 sine 4xy minus 16 xy cos of 4xy. So it looks like this answer did the product rule the reverse of what I did. No problem. Reverse order. And it looks like that's our correct one right there. Answer C. Gradient. The gradient is a vector that's the partial derivative of each component of the vector. Sometimes it could be just an algebraic form only, or if it asks at a point, you'll then plug in that point to give you the vector. And that's what it's telling you what it's doing here, but actually if a problem said find the normal vector at a point tangent plane, that is the gradient by definition. It's the normal vector tangent of a tangent plane on a surface. But it says unit normal vector, so that means we're going to have to convert the normal vector into a unit vector, which is easy enough, but we just have to realize to do that. So let's see what we have, the gradient. Let's see partial respect to x, so this term xyz will be yz. The next one will be 6xy plus 6xy. Now we go over the second component. With respect to y will be xz. The middle term, get rid of the y, we'll have 3x squared. The last term doesn't have a y, so we don't count that. The last one will be xyz, respect to z will be xy. And then plus 3x squared, x squared y, there's no z, so that will be 0. And the derivative negative z cubed will be minus 3z squared. And now we just put in 1, 1, 0 everywhere for x, y, and z. And I came up with 6, 3, 1, which would be the normal vector, but it's not the unit normal vector. We have to get the magnitude. So the magnitude of that vector is going to be the square root of 36 plus 9 plus 1, which is the square root of 46. So that means our unit normal vector then will be 6 over square root of 46, 3 over square root of 46, and 1 over the square root of 46. Looks like answer B. All right. Number 37. Find the gradient of the function at the given point. So this one doesn't require it to be converted to a normal vector, a unit normal vector. The gradient is the normal vector, so both next two problems will be just like same process. A lot of times students will have trouble with this natural log because they'll try to use log properties that don't exist. You cannot split this one up in any way, shape, or form. That's what people commonly will try to do. You just have to take, as long as you know not to do that, derivative of the log is you take the derivative of the inside with respect to whatever variable, of course, over the inside. So notice the inside parentheses here, x squared minus 7y squared plus 2z squared. That's the denominator for all three of those. Same denominator. The numerators are going to be the respective partial derivatives, x, y, z. But yeah, I see that messed up a lot, on handwritten exams when I give this problem. So the derivative, there's only one x term, so the derivative of x squared will be 2x. And only one y term, so the derivative of negative 7y squared respect to y will be negative 14y. And 2z squared respect to z will be 4z. So there's your gradient right here, gradient vector. And then we put in negative 7, negative 7, negative 7. That produces 196 on the bottom. So I just pulled out the 196. I don't know. I could have left it in there. It didn't really matter. And then I just plugged in, the negative 7 up at the top, negative 14, 98, negative 28. I don't know. Maybe I just didn't want to write 196 3 times. But then now in the final answer, then I did put each one over the 196 and simplified it down and got 1/14, negative 1/2, 1/7, which looks like B. All right, number 38. Same problem. There's only two variables this time. So the gradient vector is going to be negative 8x derivative of negative 4x squared, and the derivative of 9y respect to y will be 9. And then you plug in 8 and 3, and you'll get negative 8 times 8 is negative 64, and then 9 just stays 9 because there's no variable there. So it's going to be answer C. So let's take a look at number 39. Find the direct derivative of the function of a given point in the direction of E. So that's just the same thing as asking the directional derivative. So let's see what we have. Now the main thing to remember here is that your direction vector must be a unit vector. So most of the time it will not be a unit vector, unless it was in terms of sine and cosine maybe, but you have to convert it to unit vector. You have to remember to do that, or you will compute an incorrect directional derivative. So I renamed this U just to make it kind of fit the formula better, but keep in mind, even if they call this variable U, you don't assume that means unit vector. You can use U as just a name of a regular vector. The only vector names that have specific meanings are I, J, and K. Those are reserved labels. But anyway, this is not a unit vector, so I'll get the magnitude, which is 5, and then I'm converting it to a unit vector. So 3 over 5, negative 4 over 5. I just changed it from standard unit vector form to component form. Now we need our gradient. So derivative of 6x squared will be 12x. Negative 3y will be negative 3. So I'll put in the point, negative 6, 7, into that gradient to get a vector. And I get the vector negative 72, comma negative 3. So we take the vector we just got, gradient vector at negative 6, comma 7, and we dot that with the unit vector, and that produces our directional derivative. So it's negative 72, negative 3, dotted with 3/5, negative 4/5, and you get negative 204 over 5. I'm sure by now you probably should be comfortable with performing a dot product, so I sort of skipped the detailed explanation of that. And this question says, find the value of the minimum directional derivative. Okay, this is saying at a point, what's the smallest possible directional derivative you can have regardless of direction. Actually, the direction will be in the direction of the gradient vector, or the opposite direction for the minimum. But anyway, so you're not finding the value of a directional derivative. You're just finding what's the smallest possible directional derivative. So all you do to do that is you take it's the magnitude of the gradient. Actually, for minimum, it's the negative magnitude of the gradient, and for the maximum, it's just the gradient itself, the positive value. So you take 2x plus y that's the derivative of respect to x of this function, and then x plus 2y will be the derivative of fy component. So you put in 7, you put in 8. 2 times 7 plus 8 is 22. 7 plus 2 times 8 is 23. So the magnitude of the vector 22, 23 will be the square root of 10, 13. So the minimum value then is negative square root of 10, 13. So here you see what I'm saying is the maximum value right here be positive. So that's telling you that's the smallest possible directional derivative. So that just means, so they have to be, any directional derivative would be somewhere in the interval between those two. That means if you just made up some random direction vector, you picked a direction vector at that same point, just made up any direction vector, that's not the gradient. That's not this vector. And the answer would compute somewhere between those two numbers in that interval, because those are the smallest and largest possible numbers. Not that you have to do that, I'm just mentioning that. All right, so we're going to kind of use a chain rule. Basically, instead of using a chain rule, we're actually using a substitution method to come up with this. Instead of using and I did that in my notes section and on the other reviews and stuff, because there's really no point to actually using the chain rule for this when you can just use substitution, and that works so much more efficiently or whatever. So that all you have to do. See, x, y, and z are all functions of t, so when you substitute them into this f function, f just becomes a function of t, and there you go. You don't have to really write out the formality of the chain rule. So my numerator is going to be x minus z, so x is 2t plus 1, z is 8t minus 1, subtract that, and the bottom will be e to the t. Combine them. You get negative 6t plus 2 over e to the t. All right, so we have to do a quotient rule here. You could lift the e to the t up, but if you do, you're still going to have to do a product rule anyway. So I think in this case, to make it match the answers a little bit better, I think a quotient rule's good. Maybe not, I don't know. I didn't try the product rule. So we're taking this derivative, so it's bottom, e to the t, times the derivative of the top, which is negative 6, minus top times the derivative of the bottom, which is e to the t, over e to the t all squared, which is not e to the t squared, it's e to the 2t. Now I factored out an e to the t here, which I absolutely needed to do. Factored out that e to the t right here, because that way the e to the t over e to the 2t will take away one of those e to the t's on the bottom and leave an e to the t, and then you have negative 8 plus 6t. Now, of course, the answers are rearranged. Here they have 6t minus 8. No problem. It's the same thing as answer B. Yeah, so you always want to use the substitution. So let's see what we have here. So now we have z as a function of two variables, and now x and y are functions of two variables. So these answers will be partial derivatives. The last one was not a partial derivative because after you made the substitution, there was only one variable, t. So what's going to happen here is we're going to get, when we substitute, we're going to have u's and v's in here, which is fine. So it's going to want a u partial and a v partial. So let's be careful when we substitute here. So 3xy, x is u cos v, y is u sine v. Let's combine that together, and we get 3u squared cos v sine v. So that's the function we're going to take the u partial of and the v partial of. U partial is easy, because cos v sine v just sit there. So the derivative of 3u squared will be 6u cos v sine v. Got to do a little more work on this one. Do the 3u squared will sit there, and I'll do a product rule between these two. So it's going to be cos, if I go f, I'm going f g prime this time. Usually I go f prime g. Looks like I did the other order this time. Looks like I went, okay, sorry, Mo. Looks like I started out this way this time. Looks like I did that first. Yeah, okay. Just wanted to mention that. Cosine times the derivative of sine, which is also cosine. So you have cosine, cosine multiplied together, plus the derivative of this first cosine, or this only cosine, the derivative of this cosine is negative sine, and then times g, which is just sine. So we have 3u squared times cos squared v minus sine squared v. So it's going to be answer A. One thing I'll kind of mention here, just from a trig point of view here, that actually cosine squared v minus sine squared v is cosine of 2v. That is cosine of 2v. But the problem with this answer is, though, is that the ZU is not correct. See, this one has a correct ZU. So that's kind of weird they did it this way, but actually, I'm just saying between answer A and B, those ZVs are actually the same answer. They're mathematically equivalent. But the A has the correct U partial. All right. Equation of tangent plane. Okay, so we're going to get the gradient. Now, what we need to do on this, I mean, there's a way you can do it without it, but it's just easier if you do it this way. So f of xy is just z. So if you move this over and let it be 0 be on the left side, of course I moved 0 to the right side here. You move this over just for visual form. That's where it comes up, and we've seen this before. That's the big F means it's an implicit form. That's implicit form, and we kind of want implicit form here. You can do it without it, but I think it's better if you do implicit form. So I just moved the z over and rewrote the equation like this. So that's why I'm writing the capital F's here, because of the new function, which has the minus z right there. So in other words, the fz partial will be easy because that's -1, but we got to do some work here for the fx and the fy. Got a little quotient rule. So it's bottom times the derivative of the top, which will be 10x, minus top times the derivative of the bottom, which is 2x. And you don't have to simplify that if you don't want to, because you're just going to be plugging in the numbers 1, 1, 1, -1, 5. So you don't have to simplify that. But I did anyway, just because I saw that it was going to simplify. And the next one here, you have the bottom times the derivative of the top respect to y. 5x squared has no y, so it'll be 0. Minus 5x squared times the derivative of the bottom respect to y will be 2y. That one also tidies up a little bit. But so whether you simplify it or not, plug in 1, -1, 5 into either one of these forms, and you'll get actually get the same thing for both. You'll get 10 over 4, which reduces to 5 over 2. So what we have now, that's and then -1. So that means the normal vector for the plane components, A, B, and C, are 5 halves, and 1, -1. So it's 5 halves, and 1, minus 1. So just didn't put the 1 there. And then this, because the point's 1, -1, 5, it'll be x minus 1, y minus a minus 1, y plus 1, and then z minus 5. So now the trick is you just have to make it look like whatever answer form it's in here, so you can see the choices. If it, handwritten, that would be perfectly acceptable just to leave it like that. But this isn't too much work. I just multiplied everything by 2 to get rid of the fractions. And be careful when you distribute the negative through there, it's going to make that a positive. And then minus 5 and plus 5 cancel, so then I just kind of combine the terms, and I end up with 5x plus 5y minus 2z equals -10. So it's answer A. Number 44. Same idea, but you see they left this one in the standard form. The other form's, I believe, called the general form. Hope I didn't reverse that terminology, but I think that's right. standard forms where you have it set equal to 0 like this, where it's just not distributed through. Let's get the gradient. X squared derivative with respect to x will be 2x. No x, no x. Here's an x. Minus 2z. No other x, so that's it. The middle one, no y. Here's a y, so that'll be 3z. Here's a y plus y squared will be 2y, and then no y's left. So that's it for that one. The last one, no y on the z on the first one. Second one has a z, so its derivative will be 3y. Minus 2xz will be minus 2x, and then minus z squared will be minus 2z. Now we plug in the point 2, negative 3, negative 2 into this, and I come up with 8 minus 12 minus 9. So I have 8 times, now here's the point, so it'll be x minus 2, and then negative 12 makes it minus 12, y minus a minus 3 is plus 3, minus 9 times z minus minus 2 will be z plus 2 equals 0. So this one is left in this form, so that's why I kind of wanted to have examples in both forms, because if that question's on the final, yeah, it kind of gives you both ways to look at it. So it looks like B. Problem 48. A rectangular box with a rectangular base and no top is to have a volume of 32 cubic feet. What's the least amount of material surface area required to achieve that goal? So let's look at the function. I drew a little picture of a rectangular box there, and now we don't have a top, so we're only going to have, x times y is the area of the base. We don't have that matching area of the top because it's open. But the other ones will have coefficients of 2 to represent the sides. So we'll have a 2xz and a 2yz. And our constraint equation is xyz equals 32. So we take the lambda f, delta f equals lambda times delta g. So let's look at the partials of this function. And partial respect to x will be y and then plus 2z. Partial respect to y will be x plus 2z. Partial respect to z will be 2x plus 2y. And the other side, you'll have a partial of xyz with respect to x will be yz with the lambda. Partial of xyz with respect to y will be xz lambda. And then xyz with respect to z will be xy lambda. So here's where I did similar to, like I did in the notes. This one works well if you just do a lambda equals lambda equals lambda equals. So I solved all 3 of those for lambda right over here. And then I'm just indicating right here that equation 1 represents setting those 2 together, the first 2. And equation 2 will be setting the middle one and the third one together. Okay, so I cross-multiplied and come up with this equation right here. And the xyz's cancel, which is convenient. And then you have 2xz squared equals 2yz squared, which basically means you get rid of the 2z squareds, you have that y equals x. Same thing for the second one, you cross-multiply. And you'll have a 2xyz that cancels. We have a 2x squared z and an x squared equals x squared y. You can get rid of the x squareds, so you have 2z equals y. But I know it looks convenient that we have y in terms of the other 2, but actually the common variable needs to be solved for it. So, well, actually this one is, if y equals x, x of course equals y, and z equals y over 2. So that way when we come down to our constraint equation, everything will be in terms of y. So x equals y, that's the first y. Y is y, of course, the second one. And z is 1/2 y. Goes right here. Multiply, I didn't write it, but I multiplied both sides by 2. So you multiply both sides by 2, you'll get y cubed equals 64. And that means y equals 4. And if y equals x, x equals 4. And if z equals half of y, z will be 2. So the dimensions are 4 by 4 by 2, but then to get the actual surface area it's asking for is if you just plug 4, 4, 2 right back into this top equation right here, you'll end up with 16 plus 16 plus 16, which gives you the 48 square feet as the answer. Number 46. Using Lagrange multipliers. So our function f of xy equals x squared y. X squared plus 2y squared equals 6 is the constraint. So I'm going to have two partials here of the objective function. So the left side is the objective function. The right side will be the constraint function partial derivatives. So if consider the constraint function to be normally labeled g, so it's like basically, fx equals lambda x, lambda gx, fy equals lambda gy. So the partial with respect to x of x squared y will be 2xy equals the partial of the g will be 2x lambda. The next one will be the partial of the f with respect to y will be x squared. The partial of the g with respect to y will be 4y times your lambda. Then I just wrote the constraint function in there because now it just means you're working with an equation that has three equations, three variables, and you can solve for any combination, however you want to solve it, to come up with them. Sometimes you end up, I've done some problems where I've actually come up with a value for lambda, even though we don't really need it, but if I thought that was the best way to solve it. But anyway, this one, 2xy equals 2x lambda, that pretty much means y, if you ignore the 2x's there, that y would have to equal lambda. And then I come down to the bottom one, I have x squared equals 4y lambda, so I put y in there for lambda, so I have x squared equals 4y squared. Okay, that's very helpful, because now I can go to my constraint equation, I can replace the x squared with the 4y squared I just found, and then that turns into this, which gives me 4y squared plus 2y squared, which is 6, which gives me 6y squared equals 6. Now be careful, which is y squared equals 1, but be careful that we have two answers for this. Y squared equals 1 means y equals plus and minus 1. Now sometimes when we're doing problems, application or optimism problems of applications, measurements, things like that, we ignore, negative answers, but not here. There's nothing in this problem that says anywhere in there that x, y must be positive. Like I said, if you're getting dimensions of something, it doesn't have to tell you they have to be positive. Common sense tells you they have to be positive. So it's important we get both the plus and minus 1 here. And when y equals negative 1, that gives you 4 here. You have y, then you'll end up with y squared equals, y equals negative 1, excuse me, right here. That makes that 2. You'll get 4y squared. Wait, getting myself confused here. Let me go back. Yeah, let me go back over here. Put the 1 in there. X squared plus 2 equals 6. X squared equals 4. And then for x will be plus and minus 2. Same thing with positive 1. You put 1 back in here. And same thing with x squared plus 2 equals 6. So x squared equals 4. X equals plus and minus 2. So you actually have 4 points here to test. Now to see which one's a mins and max, you have to just plug them into the original function and just check. So you plug in negative 2 and a negative 1 into x squared y, you get negative 4. 2 negative 1 also gives you negative 4. Negative 2, 1 will give into here, will give you positive 4, and 2, 1 will give you positive 4. So actually, that's okay. In this case, we're going to have 2 answers that are the minimum and 2 answers that are the maximum. So we've got a minimum value of negative 4. when x is plus or minus 2 and y is negative 1. And we have a maximum of 4 when x is plus or minus 2 and y is positive 1. So it looks like answer B right there will be it. For 47, we've got an extra variable in there, so let's see what that's all about. Just adds another, you see here, I wrote them all out this time, so now we have a fz equals lambda z. So we have, let's see what we have here. So the partials for this objective function would be 1, 2, negative 2, right there along the left side. The partial of this one will be 2x, 2y, 2z. They all get the lambda attached to it. There's our given constraint equation. So it looks like what I did here was I just solved for the lambdas in each equation. So the top one, lambda would equal 1 over 2x, lambda equal 2 over 2y, lambda equals negative 2 over 2z. And then just basically I took the top two and went lambda equals lambda. So I kind of cross multiplied there. 4x equals 2y. So I know that x equals 1/2 y, or y equals 2x. Mainly, I probably left this there and then went back and changed this after I chose the next ones here. I'll show you what I mean. I chose the bottom. I could choose the first and the third, or the second and the third, because I just used first and second. So I used the second two here. 2 over 2y equals negative 2 over 2z. That's lambda over lambda. Now when I got y equals negative 2z, so whichever variable, and I mentioned this probably in the notes and also in the review for the video for exam 2 sample problems, whichever variable's in there at the same time, that's the one you have to solve for, not in terms of that variable. You solve, you don't solve for y, you solve the other ones in terms of y, in other words. So that's when I saw that the y was going to be the common one. I came over here and said, okay, x has to be 1/2 y, and z then has to be negative y. So that brings me down here to my constraint equation. So now they're all going to be y's, so that'll make it good. So x will be 1/2 y, that'll be squared, negative y squared. So I've got 1/4 y squared plus 2y squared equals 9. So I multiplied everything by 4 and then added. So if you multiply that by 4, you're going to get a 1y squared here, an 8y squared here. That makes 9y squared. Then, of course, 4 times 9 is 36. That gives me y squared equals 4. That gives me y equals plus and minus 2. So here I have negative 2 and positive 2 for y. So whenever x is negative 2, y is negative 2, I plug it right in there. X will be 1/2 of that y, so it'll be negative 1. And then z is the opposite sign of y. So when that's negative 2, that'll be positive 2. Then I come down here, and x is 1/2 y, so when it's positive 2, that'll be positive 1. And then z is the opposite sign of y. So here's 2 and here's negative 2. So I plug these 2 points into my original equation right here that I'm trying to optimize. And I got negative 9 and positive 9. So obviously the one that produces the smaller one's the minimum, and the one that produces the larger one's the maximum. So we have it's there's only one answer that has the 9 and the negative 9, but they also are the correct points. So you see the 1, 2, negative 2 there on bottom gives you the 9, and then negative 1, negative 2, 2 gives you the negative 9. So it is answer D. Problem 48. A rectangular box with a rectangular base and no top is to have a volume of 32 cubic feet. What's the least amount of material surface area required to achieve that goal? So let's look at the function. I drew a little picture of a rectangular box there, and now we don't have a top, so we're only going to have, x times y is the area of the base. We don't have that matching area of the top because it's open. But the other ones will have coefficients of 2 to represent the sides. So we'll have a 2xz and a 2yz. And our constraint equation is xyz equals 32. So we take the lambda f, delta f equals lambda times delta g. So let's look at the partials of this function. And partial respect to x will be y and then plus 2z. Partial respect to y will be x plus 2z. Partial respect to z will be 2x plus 2y. And the other side, you'll have a partial of xyz with respect to x will be yz with the lambda. Partial of xyz with respect to y will be xz lambda. And then xyz with respect to z will be xy lambda. So here's where I did similar to, like I did in the notes. This one works well if you just do a lambda equals lambda equals lambda equals. So I solved all three of those for lambda right over here. And then I'm just indicating right here that equation 1 represents setting those two together, the first two. And equation 2 will be setting the middle one and the third one together. Okay, so I cross-multiplied and come up with this equation right here. And the xyz's cancel, which is convenient. And then you have 2xz squared equals 2yz squared, which basically means you get rid of the two z squareds, you have that y equals x. Same thing for the second one, you cross-multiply. And you'll have a 2xyz that cancels. We have a 2x squared z and an x squared equals x squared y. You can get rid of the x squareds, so you have 2z equals y. But I know it looks convenient that we have y in terms of the other two, but actually the common variable needs to be solved for it. So, well, actually this one is, if y equals x, x of course equals y, and z equals y over 2. So that way when we come down to our constraint equation, everything will be in terms of y. So x equals y, that's the first y. Y is y, of course, the second one. And z is 1/2 y. Goes right here. Multiply, I didn't write it, but I multiplied both sides by 2. So you multiply both sides by 2, you'll get y cubed equals 64. And that means y equals 4. And if y equals x, x equals 4. And if z equals half of y, z will be 2. So the dimensions are 4 by 4 by 2, but then to get the actual surface area it's asking for is if you just plug 4, 4, 2 right back into this top equation right here, you'll end up with 16 plus 16 plus 16, which gives you the 48 square feet as the answer.